pleasure to welcome here our dear guest, Dr. Zhidenko, working now in Centro de Matematica in Universitate Federal, but I don't know what it means, ABC.
It's actually abbreviation for three cities, Santo André, São Bernardo, São Caetano. It's not that ABC that you might think.
From Brazil, okay, and he's going now to talk about traversable wormholes in general relativity. So you can start. Thank you very much.
Thank you. Well, I would like to present our works on this topic of on traversable wormholes in general relativity. And the interesting point is that we only use Einstein equations with the normal matter, like standard model matter, nothing exotic. And I will start from a short introduction, introducing some notions on wormholes. Then I will talk about the model under consideration. Then I will start from the particular case of an analytic solution of a wormhole. And we will see why actually the mirror symmetry, Z2 symmetry, should be broken in this case, and the appropriate smooth solution is actually asymmetric with respect to the wormhole's throat. And then I will talk a little bit about properties of this object, its quasi-normal rings, and briefly discuss open questions and problems related to these objects. Okay, about wormholes. In general relativity, we have space-time which is curved, which is a manifold, and that's why it's always tempting to consider some topology more interesting than usual. Yes, like this is schematically shown in this picture, the two-dimensional slice of our four-dimensional space-time, which looks like some compact object from a distance, but it's actually a portal to another point or another universe. If we look at this object from a distance from our space-time, we see something compact. But as we approach, let's say if we take a sphere with a center, this is supposing that this is spherically symmetric configuration, and we approach in this point. At some moment, we see that area of this sphere does not decrease, but starts growing. There is some point where we have minimum, let's say, area of this sphere, and this is what we shall call the throat. And after that, we are going to actually to another space-time. Yes, and well, I will not speculate about how much this is interesting, because there is science fiction about this, but let's talk about some theoretical models of how this can be actually realized. The simplest model, spherically symmetric, which was proposed by Damore and Solodukhin, is just a Schwarzschild geometry, which is asymptotically simply a geometry of spherically symmetric mass. And we cut the central part, the sphere, and glue the resulting space-time with another part. So, so we have Schwarzschild solution here and here, and at the throat we have this sphere where we connect these two space-times. And obviously, this is a solution of Einstein equations everywhere except this throat, except this sphere. But at this sphere we have a problem because, for instance, derivatives of the metric functions are discontinuous. So from the physical viewpoint, we need to put some matter there to compensate this, to describe this kind of discontinuity, to match two parts of the two sides of the throat, and this is a kind of configuration which requires special kind of matter at the throat. For instance, if we take this simple model, we have something like delta function, the infinite density of the matter at this point. And apart from this, we can think that, well, we can assume that we can put some kind of matter at the throat and have some configuration like this, because Einstein equations are local. They just relate the curvature and stress energy tensor. So at the first glance, there is nothing which can prevent us to have this kind of configuration. But it was shown in this paper by Maurice Thorne and Urt Server that actually such a configuration requires, in Einstein theory, violation of weak energy condition, namely the averaged weak energy condition along the trajectory which crosses the throat. And we know that our normal matter usually obeys weak energy conditions, so we have a problem here. And usually, in general relativity, the wormholes are supported by exotic matter, like phantom matter, for example, which is simply a matter which has negative kinetic term, which is, of course, something very exotic which we don't observe in nature. And another problem which we have in this case is that usually these configurations are dynamically unstable. If we perturb a little bit such a wormhole, it turns out that it does not come back to the initial state. It will be simply destroyed. Well, and of course, we have no experimental evidence of the wormholes, but we are talking here about theoretical models. And the question which I want to ask is if it's in principle possible to have a solution in general relativity which has the solution like this, like a wormhole. And the answer apparently is yes. I would like to start with this model, which was proposed by these guys in this paper in 2021. And the model includes the normal Einstein theory, general relativity, the electromagnetic field, the Maxwell field, and two fermion fields with mass and the same charge, with the same mass and same charge. And we consider spherically symmetric ansatz for the metric and for the Maxwell field. With this tetras, the only thing that is included here is that since we need that the radial coordinate passes twice between the throat and infinity, on two sides of the throat, it is convenient to parameterize this radial coordinate with something which is limited between, let's say, -1 and 1. If we have negative parameter x, then we consider one side of the throat, and for the positive x we have other side, and R0 is the minimum of this function, which is exactly the throat in between these two spacetimes. Okay, and also what's going on? Something really strange. Okay, so two fermions which we include here we need actually two fermions with the same mass and charge, just because otherwise we don't have spherical symmetry, because one fermion cannot be spherical, cannot have spherically symmetric configuration because of spin 1/2. And we need basically another one just to compensate to have spherical symmetry for other fields. So this ansatz allows this, and we have also this parameter kappa, which can be plus or minus. So we have this kind of symmetry, which we use a little bit later. So if we solve the well, actually, in the particular case, the corresponding equations, when charge and mass of the fermion, of both fermions, are 0, we have this analytic solution, which actually describes a wormhole, half of wormhole. In this case, we just take radial coordinate equal x. And this solution looks like overcharged Reissner-Nordstrom black hole with a charge larger than mass. This charge is topological as well as mass, actually, and from the distance, this object looks like the Reissner-Nordstrom black hole with the asymptotic charge larger than mass. But as we approach, again, we see that there is no actually black hole here. We can cross the point r equal r0 without problem for the finite time.
You said that it looks like a black hole, so there is even horizon.
From the distance. From the distance, it looks like black hole, but there is no horizon. If we approach this, we see that there is no.
Bigger than mass, it's naked singularity.
Yes, it would be naked singularity. Yes, if it was Reissner-Nordstrom, but this is not Reissner-Nordstrom solution. Okay, there is no naked singularity because r is always larger than r0. Okay. Yes, if we take this limit when our charge goes to r0, yes, then in this limit we obtain extremal Reissner-Nordstrom. So this family of solutions, just like, let's say, other part from other side of the Reissner-Nordstrom. Well, actually, this is only half of our wormhole because we need another half. And here we see a problem that we can match at point r equal r0 two sides for this function, for the metric function, and for the electric field. But fermions have discontinuity in the first derivative. Unless we can actually match the solution with kappa equal +1 and kappa equal -1, then F will be smooth. But because of this function, the other function, will have different signs, so we have this kind of discontinuity. And this symmetry, if we replace kappa by minus kappa, we actually have to do this conjugation, spinor conjugation, and we can see that this corresponds to the substitution of the fermion particles by antiparticles. So if we do this kind of match at the throat, we don't have now, like in the case of the simplest Darmouth-Solodukhin model, we don't have problems with the metric. It's continuous, and curvature is continuous. But we have to consider such a configuration that our fermions, which support our wormhole, are such that particles and antiparticles meet at the throat. So we need to put some kind of membrane to separate this, or something, add some additional conditions in order to satisfy this condition. And actually, this particular solution has another problem, that is, we cannot have normalizable solution in this case, because, for instance, for kappa equal 1, asymptotically this goes to 0, but this remains finite. So our fermions are not localized at some place. They are like everywhere in the universe. We cannot normalize this function, which is also not natural. But this latter problem is solved when we consider non-zero fermion mass. If we have non-zero fermion mass, the fermions become short-ranged, and it turns out that they are localized close to the wormhole's throat. Of course, we don't have the analytic solution in this case, but numerically we can find that if we solve the equation in one part for the non-zero mass, and do this kind of match at the throat at x equal to 0, we have smooth metric functions and electric field, and we have discontinuity in the fermion. So this first problem with the discontinuity remains. We need to separate somehow particles and antiparticles, and this is basically the reason why we cannot have the mirror symmetry. So at the first glance we have connection between two space-times, yes, and everything is symmetric. But once we use fermions to support the wormhole, we cannot maintain it symmetric, maintain it the mirror symmetry between these two parts. We need to break this, and we can do this. We can solve. Well, this is the summary, that we can see that the charge density, for example, changes its sign at the throat. So if we consider this kind of symmetry, if we want to preserve this kind of symmetry, we need still to add something at the throat. So the idea is to not to maintain this mirror symmetry between two sides of the throat, and solve simply the system of equations in the whole space-time in both directions.
I would like just small comment that everything that was before that on Z2 symmetry wormhole is what was done in that first paper that Sasha mentioned in physical letters by Blaskis and Evgen and others. And actually this means that when he said that we need to add additional matter, that means basically that solution is not only discontinuous, but also is not solution of the system, because you need to add something to the system to satisfy the equations.
Well, technically it is solution everywhere except the throat.
Except the throat. So it's not a solution in the space.
Yeah.
Okay, so what happens next? If we solve our system of equations in both sides, yes, without any matching, we of course break in the symmetry. We can consider the initial conditions at the throat, which are basically values of the function n, derivative of the function b, and values of the fermionic functions. Yes, and if we fix ni and bi and vary these two functions, we see that our solutions have problems at both infinities. Usually they diverge like this, except for some particular values of fi and gi. And how do we know numerically that these values exist? We can see that if we vary these two parameters, gi and fi, the asymptotic differs at, for example, at the edge between blue and green. Between blue and green, we have difference in the function g at +1, and function f at x goes to -1. And actually, what happens? The sign of one of these functions changes along to one of this curve, and the sign of the other changes along to another. And at the intersection, we can conclude that both signs change. So we have one single point where both of these functions are 0 at the infinity. So we have normalized configuration of the fermions. And well, after we do this, we can read off the parameters of the solution. We can find that well, basically this parameter ni is just a scale. It's just a units of measurement for the time. So it doesn't matter. We can always choose it arbitrary, like we want. And this parameter bi actually parameterizes our family of solutions, which have which are wormholes with different value of asymptotic mass and topological charge. As bi grows, we have configuration more different from the extreme Reissner-Nordstrom. Well, and we also impose this additional condition, which means simply that if we put an observer, or let's say anything, at the throat, it will not experience force if it stays there. So it's like free-falling observer, stationary free-falling observer at the point of throat. So in this case, we have three types of such observers in this case. We have two asymptotic observers on both sides of the wormhole, and another one in the exactly at the throat. And all this, what is interesting, that all these observers are redshifted one with respect to another. So well, this is just an example for a particular combination of the parameters, yes. And we see that we can have for the given parameters, for the given charge, mass and BI, we have also different solutions correspond to different intersections. This point, for example, and this point. And well, probably we have infinitely many, but other solutions are much harder to localize numerically. And we see that the configuration of the fermions is quite different, but the metric functions and electric field remain very close. And also what is interesting is that this asymptotic behavior is different on two sides of the wormhole. The asymptotic observers are redshifted. It is small redshift for the considered family, but if we consider some other condition, additional condition at the throat, if we don't have this this point of free-falling stationary observer at the throat, but at some other point, which was considered in this page, then we can have even more symmetric wormholes, and well, particularly we can have asymmetric solutions without redshift, probably between asymptotic observers. But in this case, at the throat, the free-falling observer is not stationary. It's some other point. Okay, so one more comment about geometry of the wormhole. We have this topological charge and mass, which we can measure at a distance. Yes, when it looks like close to the overcharged Reissner-Nordstrom geometry. But these quantities are actually topological. It means that in fact, they have no source. If we look from the distance, we can localize the let's say source of our electric field and gravitational attraction. But as we go there, we just cross the wormhole and we find no actual source. Our electric field, for instance, it goes from one universe to another, yes, crosses the throat and does not have any source. Well, similar thing with the mass. So how this kind of configuration can appear is also interesting. Sorry. And as I already said, that if you consider two asymptotic observers on different space, on two sides of the wormhole, they are usually redshifted. This redshift is not very large, but still exists. And also, this theorem about weak energy condition is satisfied. So we can conclude that our fermions in this configuration actually violate the weak energy condition, which we don't observe naturally in the laboratory. And of course, the most relevant solution would be when we have zero charge, because we need two different fields, two different fermion fields with the same mass and same charge. And we don't have, if we consider, for instance, electrons, we don't have another particle with the same mass at the same charge. Muons, for instance, have larger mass. But for neutrinos, we can expect that the masses are equal, and this gives us estimation for the size of the solutions which we found, and it is actually macroscopic size, and these estimations is obtained from the estimation of the Compton length of the neutrinos, and of course it can be larger, yes, because this is the estimation from above, from below, yes. So we could expect that we can have this kind of solutions in nature. We also studied the rundown for such objects. We considered the test scalar field in this background, and we see that the signal initially it is practically indistinguishable from the extremal Reissner-Nordström. It's slightly different. But the crucial difference is that we have the so-called echoes. We have repeating of the signal at after a certain amount of time, and it continues to the rundown appears again and again. It's slightly different, but still. And of course, the same phenomenon we can observe from two sides of the well, actually not we, but probably there is another observer on the other side of the wormhole. And the difference is that the same signal will look differently because of the redshift. Yes, we have, for example, this one, the redshifted observer sees the time difference between these peaks shorter, yes, for this observer. And the reason why these peaks, which are called echoes, appear is that exactly because of the difference between our configuration and the Reissner-Nordström black hole. For the Reissner-Nordström black hole, if you write down the Klein-Gordon equation, we see that there is an effective potential with one peak, yes, and this one peak manifests itself at the beginning when we see the rundown, which is similar to the Reissner-Nordström. But then our signal goes inside the throat, goes to another side, to another universe, and reflects from another peak. And this reflected wave is scattered again at this potential, and we see second peak, and this process repeats because it can go back and forth many times. Actually, every time the amplitude will be lower, but still it's not so it does not decay so fast as usually happens for the echoes if we, for example, consider quantum corrections to the black hole horizon. Okay, so to conclude this talk, I would like to tell a little bit about open questions related to this solution. Well, first of all, we did not consider the gravitational perturbations of this black hole, this wormhole, and so we need to know if it's actually stable. And if we are talking about spherically symmetric family of perturbations, there is kind of indication that it should be stable because of the character of the behavior of the fermion fields if we slightly change the initial conditions for the solution at the throat. If we slightly change it, then fermions grow infinitely, and that means that we need infinite energy to change this configuration like this. But of course, this does not mean that this configuration is stable, because of we can consider perturbations which are not spherically symmetric, and these perturbations might be unstable because of fine-tuning of these two fermions which we have in the beginning. We choose this ansatz in such a way to have spherical symmetry in order to have the simplest solution. And of course, if we change a little bit, the configuration can be unstable. Yes. So it is quite probable that actually we cannot maintain spherical symmetry as well if we want to have a stable configuration of the wormhole supported by fermions. And well, once we are breaking spherical symmetry, probably there is no need to consider two different fermion fields. We can have a more viable configuration with just one fermion field. At least what Jose Blasquez Salcedo told me, that he's optimistic about this, but this is a way much more complicated model, which should be the equations will be, in this case, not spherically symmetric, and sorry? Perhaps axial symmetry would be enough, but again, nobody knows. Should be studied. This question should be studied. And another point which I not quite understand is that actually classical Dirac field is not what we observe. We usually work with particles. So this what we have in the experiment is quantized field, right? And I'm not sure if it's possible to quantize this model, because we don't know the quantum gravity. So this is another problem which is not clear for me. But my understanding is that this could be actually an approximation, because we know that let's say that neutrino field behaves like a field if we look at the wind from our sun. We see, for example, the oscillation of neutrinos, etc. So perhaps this is not a bad approximation, but still not really does not match really the experiment. Well, that's it. Thank you for attention. If you have